Piper picked the peck of pickled peppers? Does Peter Piper pick the peck of pickled peppers? Wait, how many? Wait. No, it's like how much pickled peppers did Peter Piper pickled peppers?
Hello and welcome back to Calculus2 with pickled peppers and everything else that was running in the background, sponsored by a friend here, Alex, right?
What's up?
Happy? We started the class. So let's talk a little bit about series, focusing on infinite series. So last time, as you don't know because you probably didn't look at it at all because the exam doesn't include it. Now I should include that in the exam, which means it becomes relevant and then you should look at it. Well, we can vote later. Anyway, first lecture on chapter 8 was sections 8.1, 8.2, which combined knowledge on sequences. And we defined the sequence as the ordered list of numbers. And since it's a list of numbers, we separate members of that list by commas. So we had a sequence defined as ordered list of numbers. And then we had, let's say, an that you would write as a0, a1, a2, a3, and so on, going to infinity. Now we are going to go a step further, and we are going to define series. Series is a sum of a sequence. So now we are introducing a summation symbol, Greek letter sigma, which is equivalent to our capital S. It looks like this. It stands for sum. So this is sigma. It stands for sum. You know that obviously from a Calc 1 class, but that's okay. I'll still write it. And what we had before is that if you have that your an is equal to n, which had, let's start at 0, and then 1, and then 2, and then 3, and then 4, 5, and so on, you will have summation of an, which in this case is summation of n, which starts at 0, goes to infinity. So you will write those limits right there. And that is going to be 0 plus 1 plus 2 plus 3 plus 4 plus 5, going on forever. So what I have here is visual representation of the difference between sequence and the summation, which is a series. So up there you can have just an, which is 0, 1, 2, 3, 4, 5, and then let's say you have sum of an, which is 0 plus 1 plus 2 plus 3.
On the first sigma, is it 0 to infinity or is it n to infinity because it's sub n?
Well, it's n equals 0. So n is the counter, right? So n equals 0 to infinity, and then you start plugging them in. You use the lowercase I in Calculus 1. So for another example, we could use, let's say, summation of 2 over n squared, right? You have this. And let's start at 1 and go to infinity. You can't really start at 0, right? Because then you would have 2 over 0. So this would be 2 over 1 plus 2 over 4 plus 2 over 9 plus 2 over 16 plus, and it will go on forever. So we can have any kind of formula, and we will be plugging in these values. N Air quotation marks is the main variable for the problem, the independent, but we know it's a discrete counter. Since sequence is ordered list of numbers and series the sum of the sequence was ordered, that ordering is inherited by the series. Series is ordered as well because it has this some kind of formula that developed into it. Okay, so now what kind of series do we have? So series divide into finite and infinite. These finite ones, not interesting. Finite series, like let's say summation from 2 to 5 of n squared minus 2, you can compute that. And if you're annoyed that it has too many terms, you will write a code with a loop and it will add it for you. 3 lines, all right? So finite series are not interesting because they always converge and you can always write a 3-line code to add them regardless of how many finite terms they have. So we don't bother with finite series ever. So in this case, finite series you would have, so 2 squared is 4, minus 2 is 2, plus 3 squared is 9, minus 2 is 7, plus 4 squared is 16, minus 2 is 14, plus 5 squared is 25, minus 2 is 23, and you add all of these numbers and you get the answer. So that's 30, 46. So finite series always converge because you have finite amount of numbers to add. You know, it could be 46, it could be in thousands, in millions, in billions, it doesn't matter. They always converge, not interesting. What we are interested in is this notion of infinite series where you have to add infinitely many numbers. And now when you have infinite series, that one could either converge or diverge. Converge means it adds to a finite number. So convergent series adds to a number or a value. In the divergent one shoots off to infinity. Divergent adds to infinity. And those are the only ones that are interesting to study. Now we have 10 tests that will tell us whether the infinite series converge or diverge. Now, some of these tests will be able to tell us the sum, and those are the first 2 that we learn. Other 8 will tell us about divergence or convergence, but they will not be able to tell us what is the value they converge to. So I would know that a certain series converges, but I don't know what it converges to. So I will have to use some other mathematical means and techniques to figure that out. Note that for infinite series, you are always adding infinitely many numbers. So this is the first time where you get to see that you are supposed to retire your common sense and intuition to some degree. Because if you're adding infinitely many numbers and they're all positive, you kind of want to think that all of that adds to infinity, so why bother with the entire chapter, right? But that's not the case. If I have 1 over x squared, n squared, if you add that from 1 to infinity, it will not add to infinity. It will add to certain value, which you can actually compute. Well, not in this class. So you will see that summation of 1 over n diverges, and the summation of 1 over n squared, or n cubed, or 1 over n to the 10th all converge. And we are going to have a test called P-series, which will detect that. You don't know what it converges to, but you know that it does converge, and it has that single value, which is the sum of the entire thing. Moving on, we are, the way we learn these tests, so we're going to cover 4 sections, and we will learn multiple tests in each one. Now, the same way like integration, you look at the problem and you say, okay, this is integration by parts, this is integration by partial fraction decomposition, or so on. You will have to know these 10 tests, and then you will recognize whether it's the integral test or ratio test or root test or comparison and so on. So we're going to have 10 different tests. I'm telling you this again. You have to memorize those tests verbatim, and most of these problems, they're all proofs, obviously. Most of these problems will literally be you writing a little paragraph proof or something. Sometimes you will calculate stuff. Integral tests will involve you with working on those improper integrals that will have 0 to infinity in limits. So there will be calculations as well, but most of the time is going to be logic and writing, and for the most amount of time you will be shoveling algebra. So that's another part to this. So what do we have? We have idea of a sequence, which is the ordered list of numbers. Then if you add those numbers, you get the series. To denote the series, you put the sum in front of the sequence and say, I'm summing the sequence. And then it can be finite or infinite. Finite ones are boring and not interesting because they always add to a finite value, so they always converge. It's the infinite ones that we study and work. So now, what are the 2 tests that we are learning today? The first one is called geometric series test. Geometric series test. All right, so what's happening with that one? No coughing. Well, help it. I had this. I don't know what I did with it. Give me 1 second before I was just looking for something, but I can't find it. I think I'm gonna give up. All right, so let's talk about geometric series test. So, if you have series that looks like this, summation of a r to the n, where n starts at 0 and goes to infinity. So if you can put it in this form, right? That's the geometric series. Right, so if you have that, then this is what happens. If r is in between -1 and +1, we have convergence. And if r is larger or equal than 1 or smaller or equal than 1, the negative one, sorry, we have divergence. And if it converges, the sum is equal to A over 1 minus R. It's a formula. All right. So I hope that you see that if you don't memorize this, you are doomed. Because the problem looks like this. Test for convergence, 1/2 to the n, from 0 to infinity. This is how problem looks like. And the solution is r equals 1/2, which is less than 1, converges by geometric series test. Done. That's it. The problem is solved. So if you did not memorize the test, there's nothing that you can do. You're not going to sit there and go, okay, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 forever to come up with the answer. You are memorizing these conditions here for convergence and divergence. And if it doesn't, it has to fit one of those two. So it is as simple as you use your eyes and you look at it. Alex first.
Would you say S means?
Sum. I'm going to compute that for this.
Okay.
Nick.
How do we know the difference between A and R?
That will come up with more examples. We are going to do at least 5 or 6 more. Yes? Beautiful. Since I have convergence and this is geometric series, I can calculate the sum. Now we see that A is actually 1 in front of 1/2 because 1/2 is R. So I will have A is equal to 1, R is equal to 1/2, so sum is equal to 1 over 1 minus 1/2, which is clearly 2. So when you add infinitely many values of this particular geometric series, it adds to 2. That's the sum of it. So it converges to 2. Bueno? The next question is, how do I know stuff in terms of A and R and so on? So here's another one. Summation 0 to infinity for, let's say, 3. Let's do it this way. 3 over 5 to the n. That's it. 3 over 5 to the n. That's the problem. You immediately understand that this 3 is something that you put here, and then you have your 1/5 to the n, and you have your A is 5, and R is 1/5. A is 3, and R is 1/5. 1/5 is less than 1. We have a convergence. So summation is 3 over 1 minus 1/5, which is clearly 15/4. Yes.
Okay, so if it was 3/5 all to the power of n, then A would be 1 and R would be 3/5?
Beautiful. So the next problem is what's happening if it was 3/5 everything to the n. In this case, A is equal to 1, R is equal to 3/5. 3/5 is still smaller than 1. We have a convergence. So summation for that one is 1 over 1 minus 3/5, which is clearly 5/2. Right, when you compute. So this is not just we're talking about exam 3. We're talking about exam 3. We're talking about final. We're talking about differential equations. Guys, you have to memorize these tests. Everything that I do put into these box, yeah, flashcards, whatever it works, black magic, whatever. Just get it done that way so that you can, as soon as you see a problem, you know immediately what to write. We don't get to calculate and think about too many things here. It is, you see the form, you go for it. Next question. Summation of e to the n, 0 to infinity. Why? Value of e is larger than 1. So r is equal to e, which is bigger than 1. That falls into this category here, right? Right there, r bigger than 1. So it diverges. We don't get to compute the sum, obviously, because they do add to infinity. So summation of e to the n diverges. Now, what am I adding? I'm adding e to the 0, which is 1. So 1 plus e squared plus e cubed plus e to the 4th plus e to the 5, and so on. I add them all to infinity, and they do add to infinity. So you see that when you do this one, it's going to be 1 plus 3/5 plus 9/25 plus 27 over 125, right? Plus 81 over 625, and so on. When you keep adding those, infinitely many, they add to 5/2, they converge. The one below diverges. Where? Which problem? A equals 1? It's right here, because there is no, this entire thing is R.
Oh, okay.
So the coefficient in front, if it's nothing there, it's 1. If you have a number, it's that number. Evil laugh, right? All right, let's do one more. Yes?
What exactly is, like, what exactly are you finding with the summation? That's what I'm a bit confused about. Like, you add...
Well, I will define that very, very soon. So let's do one more problem, and then we will talk more about what it means to converge and diverge and write some more definitions. So here is one more thing. So let's go. Summation 1 to infinity of 1/3 to the n. So what's the sum? Let's see. I mean, does it converge? Does it diverge? And, you know, all of that stuff.
I cannot read it on the long.
Okay, so let's talk about this problem. This is a very evil problem. It's very evil of me to ask this because obviously I didn't talk about, well, I did talk about it, but I did not make a big deal of it yet. And this is the time for me to make a big deal out of it. So let's make it big. Do I have n? I do have n. Do I have r? I do have r. Do I have a? That's the one. Is it infinity? Yes. And then what do we have here? We have a problem, okay? So this is why memorizing these things and making sure that they are identical, otherwise formulas and rules do not apply or do not hold. So the issue with this particular geometric series is that it doesn't start at 0, which definition requires for our formula S equals A over 1 minus R to work. Therefore, I have to do something that it's called shifting the counter in order for me to bring it back to 0. So what I'm going to do is I'm going to subtract 1 on both sides under the sum. And my next step here is summation n minus 1 is equal to 0 to infinity of 1/3 to the n. Now we're all happy with that because now summation does start at 0, but look, we have n minus 1. Convenient substitution, k equals n minus 1. To make that now into k goes from 0 to infinity, but then I have to change this n here, right? And that n is k plus 1. So the new exponent becomes k plus 1. So think of it as the substitution kind of deal, where we transform from n to k so that we can have our counter start at 0. But the issue now is the exponent, because the exponent is now k plus 1, and that doesn't match our formula anymore because it was a r to the n. But luckily, this plus 1 is easy to deal with because you can just peel off 1/3, right? So we use basic algebra and have 1/3 times 1/3 to the k. K goes from 0 to infinity. Look, your a is no longer 1. It's now 1/3, right? Do you agree that this 1/3 has the exponent of 1? And when I multiply it, it will be k plus 1? So that's when I say peel off. That's what I mean, right? I mean you bring 1 in front. So now a is equal to 1/3. R is equal to 1/3. Well, clearly converges, right? Because 1/3 is less than 1. And I have summation to be 1/3 divided by 1 minus 1/3. So that's going to be times 3, so that's 3 over 3 minus 1, so 3/2. Do what? Oh, sorry, it would be 1. Yeah, it's 1/2. Sorry, 1/2. When I multiply top and bottom by 3 to get rid of the double fraction, it becomes 1 over 3 minus 1, and that's 1/2. So it adds to 1/2. So I just wanted you to see the process of how we deal with these series. So the possible answers are converges or diverges. Converges means it adds to a finite number, in this case 1/2. Diverges means adds to infinity. You've seen that you have to be very careful with memorizing definition, memorizing every aspect of that definition, because anything could be off, and then the theorem you learned, the test you learned would not work. So in our problem, this was 1. It could be 3, right? So you have to shift 3, and so on. This is not isolated thing that you just need to pass for Calc 1 because Calc 3 doesn't have it. That's true. Calc 3 does not have this. But differential equations do. And I already showed you some of the stuff, but this thing over here, these are power series, so that's the next step up. But you can see this issue of the counter starting at 0, counter starting at 1, counter starting at 2, and sometimes I have to use these forms, but I also have the ones that are shifted. So you see that over here the exponents don't match, right? And the counters don't match. And over here, all of these match and these match. So you would think that these are the ones that are preferred to use, but some cases we'll have to use the original ones, which is, as you can see, exactly what I used. I used the original ones because when I distribute x squared, that fixes the problem with the exponent. And then for the counter, you can peel off. So in order to understand and navigate like this through differential equations, you have to start with, the baby step first, right? And the baby step is shifting the counter when we only worry about one thing at a time. So you are going to see this again and again on a larger scale. So learn it, don't just try to pass it. Now, what is actually going on? That's the biggest question, right? So now you've seen a little bit of calculations, and now the almighty question, what the hell is going on? So, as I said before, we are exploring mathematical concept which adds infinitely many numbers. So that's it. Now, those numbers are ordered because of the sequence, and we want to know if those numbers add to infinity or add to a finite value. Finite values lead to finite energy, finite charge, finite this, finite that. Divergent one lead to explosions and things like that. Now, if you want to work in a field of mathematics of detonation, you will be looking for divergence, right? But if you are trying to build a cell phone or something, you are looking for convergence, okay? So all of these things are relevant. Now, let's see. I told you earlier what is the meaning of the whole thing in terms of the summation. So I told you that you are adding the sequence. So if you are to look at the geometric series, let's say 1/2 to the n, and 0 to infinity, I already told you what this becomes, right? It is 1. When you plug in 0, 1/2 to the 0 is 1. Plus, now n becomes 1, so it's 1/2, plus 1/4, plus 8, plus 1/16, plus 1/32, plus 1/64, plus, and it's gonna go like that forever. Now, what does, and this is now new piece that you should focus on, what does it mean for a series to converge? Well, I told you that if it converges, it gets the answer, like 2 or 5, right? But the theorem for convergence of series is actually series converges if the sequence of partial sums converges. Now, this is something that, we don't really use, but it explains what's happening. Let me write the sequence of partial sums. So S0 is just 1. S1 is 1 plus 1/2, which is 3/2. I'm looking at my numbers up there. So now I have to add first 3 numbers, common denominator, so that's 3/4, 7/4. So 1 plus 1/2 plus 3/4 is altogether 7/4. Then S3 is equal to 1 plus 1/2 plus 1/4 plus 1/8. So that's going to be a denominator of 8. So I have 8 plus 4 is 12 plus 2 is 14, 13. So 13/8. Then I have the next partial sum, which is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. And that one is on a 16, so 16 and 8 is 24. and 4 is 28, 30, 31 over 16. Or you just take your calculator and calculate. I think it's 31. So that's a 16 on the first. So 16 and 8 is 24. And 4 is 28. 30, 31. Yeah, 31. Now, this is called a sequence of partial sums. Why is a partial sum? Because I'm only using first term and then the first two and then the next, right? And the next, so first 3, first 4, first 5, and so on. It creates, they're called partial sums because if you look at one of these, right, you throw this away, right? So you're partially adding the numbers. You just add this many, and then the next step you add this many, and then, right, you keep including more and more. So now, sequence of partial sums. In this case is 1, 3/2, 7/4, 13/8, 31 over 16, going on forever. And if you are careful about this, you can actually put this together and then use the limit test from the last class, and you will see that the whole thing converges. So if the sequence partial sums converges, then the series that it came from converges as well. So I can work this out into a formula, I hope. Let me see if I can work this out into a formula. Bottom is easy. Bottom is very easy because the bottom we have just 2 to the n. So an is equal to, bottom is a to the n, and we start our n at 0, right? Now what's the top? The question is, right, how do you think about these things? Looking at the top, is there a way for me to kind of figure out what's happening there? 3, 7, 13, 31. Well, they're all primes. Congratulations on that one. Can't factor anything from them, obviously, because they're all prime. Then I start playing with numbers to see if they're going to fit any pattern. I see that number 3 is 1 away from 4, which can be written as x squared, well, n squared, right? I also see that 7 is 2 away from 9, so if this was 2 squared, then this is 3 squared. Then 13 is 3 units from 16, which is 4 squared. Now 31 is 4 units from 35, and that breaks the pattern. Unless it was 32, which would make 36. No. Can that be a 25 there? Did I add this correctly? Yeah. I did that correctly. Right? So it breaks pattern. So it's not that. But you can see that, yeah, so we can't put this together easily.
S3, 15,
Do what?
Is it S3,
15 eighths?
Yeah.
It is? 15 over here? Like this?
Yeah.
All right. Thank you.
The pattern was already broken.
Yeah. The hell?
I was thinking times plus 2.
How to
Plus 1 half.
right?
What happened?
Like
1/9, still 1/8.
There's no 1 over 9 anywhere.
What's supposed to be 1/9, like 1/2, 1/4? It's according to it.
1/2, 1. This one?
Yeah.
It's 31 over 16.
Like, no, it's supposed to be 1/2 plus 1/4 plus 1/9, right?
Why? It has to be 1 plus for the 0th term. If you start at 0,
Yeah,
right?
if it's 1, there will be 1/2. No.
Because right you start, it's going to be n equals 0 produces 1, n equals 1 produces a half, and so on. Yes?
2 to the n minus 1, I think it was.
Over n.
No, you see
The pattern?
the pattern is 2, 4, 8, 16, so it's like
Ooh,
difference
2,
between
4, 8.
16, you know, the difference between the see that?
2n minus 1. No, it's 2 to the n on the bottom. 2n minus 1 on top? Let's see 0. So if I plug in 0,
Wait, 2 to the n. Like,
2 to the
2 to
n.
the n power. Plus 1 or minus 1?
how's it going to be minus 1?
Is this something we're going to have to do?
Yes.
Okay.
It's plus 1, guys, because if the first one is 0, then 2 to the 0 is 1. Whoa. It doesn't work.
Wait. Hang on. It's 2. 2 to the, it would just be 2n minus 1. 2 to the, Wow, what?
Start n equals 0. All right, so 2 to the n, so that's going to be 2 minus 1 is 1. And then when it's 1, it's going to be 4 minus 1 is 3. And then when it's 2, that's 3, it's 8 minus 1 is 7. That's it. That's it. He came in and it goes like, done. See that?
Trying to see why he doesn't like these.
Nice. All right, so we have the an, and now you take the limit of this and it converges to 1, right? So since the limit converges for the sequence then of partial sums, then the series that came from converges. Now obviously computing this every time, holy nightmare. That's why we have 10 tests. You're gonna go and you say, oh my god, I have to memorize all this crap? Yeah, because you memorized multiplication table, you memorized the derivative rules, you know the derivative of sine is cosine, you don't go do the limit proof every time you need it, right? You memorize these things because those were shortcuts. This method will always work. You get any kind of series from chapter 8, you write out a sequence of partial sums, you compute this, and then go on and put this together, and then take its limit to see whether it converges or diverges. Or memorize this rule and be done like that. Oh, R is less than 1, converges. Oh, R is bigger than 1, diverges because I memorized it. All right? So I understand that there is, 10 tests coming up for memorization, but that's a shortcut and much less work than doing this for every problem under the sun. Now, Nick, did I answer your question in terms of what the hell is going on in terms of what are we doing at all? Not really? Okay, I'll try one more time, and then again, if needed. So we are adding infinitely many numbers, and we are trying to see whether that adds to a finite value or to infinite value. That's it. That's what we're doing in the entire chapter. And we're going to do the same thing with functions on the next one. So, yeah, it goes like that. So, that's that. Now, summation of 3 to the n minus 5 to the n over 4 to the n from 0 to infinity. Does this converge or diverge? I love the answer of yes. That's
Is this where you're going to teach us another method? Or
no.
oh boy.
No negative numbers here. Did you just subtract 3 and 5? I'm going to go and jump off a bridge. Where's the closest bridge where I'll definitely die if I jump off of it?
Jump off the desk.
Yeah, that's a drive, right? That's a drive away, man. You gotta. Why is that?
All right, stop talking about the bridge. Let's go over here and look. You cannot subtract. These are exponents. Yes? You separate into two sums. Yes. So the two sums will be subtracted. These are the favorite NGIT problems for exams. They love it. So this is 3 to the n over 4 to the n minus summation of 5 to the n over 4 to the n. Both of these 0 to infinity. So each one gets its own sum. And further, using the, and I know. No, all I need to do is wait. I don't, see, the beautiful thing now is I don't even have to touch it, right? It's, look at that. It's like, ooh, done. It's getting better. So, 3/4 to the n minus 0 to infinity 5/4 to the n. So what do we know? Uh-huh. So 5 over 4 is bigger than 1. Make it crisp. So 5 over 4 is bigger than 1. So what happens when you add a number or subtract a number from infinity? It's still infinity. So as long as one of these explodes, the whole problem explodes. Therefore, this diverges because the second one diverges. Bam. Because. All right? So the first one will converge. The second one diverges. Because that one diverged, the whole thing is gone. Done deal, right? Now your textbook might have some of the, more interesting and less user-friendly problems, which let me see what we can master from here. So here is the problem from the textbook. Find the sum. Oops. Find the sum. So this is problem 32. Maybe we should do. Let's do 2 examples. 2 more. So how about this one? Summation 2 to the negative 3k from 1 to infinity. Let's start there. This is your textbook, which is why I told you get Larson, but you haven't. I can do. So let's start with this. I'll give you the book back after the message. Just by looking at this, does it converge or diverge? Did you just use the word obviously?
Very quiet.
Sure does.
What did you say?
it diverges with the one greater than
What's greater than 1?
1.
Hell no, it's 1/8. What do you mean?
If there's one like that, like
You clearly see that the r is 1/8. I understand that all of you are calculus masters. Now I need your middle school skills. That's what I need in this chapter out of you. All right? So, find that middle school strength that you stashed away a long time ago. Let's start rewriting this as we have 2 to the negative 3 everything raised to the k, because that's power of exponents. And then we are going to apply minus sign, which would make this 1 to the 2 cube positive in denominator, which will eventually tell us 1 to infinity, as I said, 1/8 to the k, which is clearly convergent because we memorized the test, right? Because 1/8 is less than 1. But then, yeah, it starts at 1, so to add a little bit annoyance there, we will have to peel off 1, so that's going to be 0 to infinity 1/8. 1/8 to the k. And a is equal to 1/8. R is equal to 1/8. So we know it converges, right? The sum is 1/8 divided by 1 minus 1/8 times 8. So that's 1/8 minus 1. So it's 1/7. It adds to 1/7, the whole thing. Was there a clearly diverges?
Yes, obviously. Obviously, sorry. Obviously.
Guys, think twice. For the entire chapter, think twice. And try to avoid obviously, clearly, and all of those, because it gets to be really tricky and evil quickly. Use the force of algebra. Now let's try another one of these clearly problems. Or obviously. All right, so what can you tell me about this? Okay, so clearly or no?
Obviously, it diverges.
Obviously diverges. All right, so we have 1.01 raised to the n, starting from 0 to infinity. So divergence because r is 1.01, which is bigger than 1. Done deal, right? Awesome, right? There we go. So test number 1, done. You are all masters of geometric series. How's your telescoping series? Let's check.
A little rusty.
Telescoping series were not a major focus point of your textbook. They are kind of wrapped in like 2 examples, a little bit on a margin of a page, and that's it. But then they give you, 30 exercises to work out. Telescoping series are the series where you get to look at the difference between 2 series. So they look like this. Or the counter could be n plus 2 or n plus 3 or anything like that. So, and this can start anywhere, 0, 1, 2, that doesn't matter where it starts. So, telescoping series is not a rule where you look at R or anything like that, because there's no R. It is a procedure that you do. And if it works out, it works out. If it doesn't work out, then you're doomed. So you will know it when you see a subtraction, right? That's how you will know it. So I will immediately give you the introductory example for telescoping series. I'll just put this in a exaggeration box. So for telescoping series, let's take a look at the summation, let's say from 1 to infinity of 1 over n minus 1 over n plus 1. So this is called telescoping series. And this is how it works. We are going to start writing these terms out. You're going to write this for 1, plus, write it for 2, plus, write it for 3, plus, write it for n equals to 4, and so on. So you write it for 3, 4, 5 terms. We'll see what will tell you to stop. So you write this few times, and then you say, I'm getting bored. So let me just go all the way to infinity by cheating and saying that my last term is going to be 1 over k minus 1 over k plus 1, and I'm going to send that k to infinity instead. So what am I going to do is I'm going to write finite amount of these. Look for some pattern, we'll see that. And then instead of actually plugging all of the numbers up to infinity, I'm going to replace n with k and send k to infinity. So this k becomes a finite value that I can compute, and then I'm going to send that k to infinity and see what happens. So let's write this out, see how it works. So the first term is when it's equal to 1, so I have 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 plus 1 over 4 minus 1 over 5 plus 1 over 5 minus 1 over 6 plus, and this is where I'm getting bored now. So what I'm going to do is I'm going to start writing out some of these terms that are air quotation marks at the end of this addition, infinite addition. And those would be, I'm going to write them from behind. So I'm going to put a setup for, let's say, 4 of them. And then I'm going to write them from behind. I'm going to write the last one first, because that one is going to mimic my original one, like this, except it's with k's. And the one before that one, the counter goes down by 1, so it's 1 over k minus 1 minus 1 over k. then it's 1 over k minus 2 minus 1 over k minus 1, and then 1 over k minus 3 minus 1 over k minus 2. So you see how, if you observe here, 1 over 1 becomes 1/2, becomes 1/3, so it's like 1 over 1, 2, 3, 4, going up by 1 each time. And this guy also becomes 1/2, 1/3, 1/4, 1/5, 1/6, right? So you see how it's increased by 1. Every next term is plus 1, because clearly, right, this one goes 1, 2, 3, 4, 5. Now, going backwards, it's minus 1, right? So 1 over k, then 1 over k minus 1, 1 over k minus 2, 1 over k minus 3. You see that pattern, right? So what I did is I write out a few terms in the beginning, and then I write, in quotation marks, the last few terms. Now, it doesn't take a PhD in nuclear physics to figure out that a whole bunch of stuff cancels. You can hunt positive and negative half. Dead. Positive and negative third. Dead. Positive and negative quarter and a fifth. And by the pattern, this negative sixth, even I don't see, plus 1 over 6, the next parenthesis will have it, right? You just follow the pattern. Now go backwards. Dead, 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 and by the same token, this one would be dead. What's left? But remember, this k has to go to infinity, right? You still have to do that. So what's the answer for the sum when I was adding these terms, right? The answer is 1. 1. Let me just circle the 1 plus the limit of negative over here as k goes to infinity of negative 1 over k plus 1. Now that happens to be 0, so the whole thing adds to 1. I just added infinitely many numbers. Telescoping series works because there is a minus over here. So all of these cancellations can happen. If you have a plus there, diverges right away, right? Because they just keep adding. Or use a different method. You have a minus there, there is a chance of convergence, and look, at the end you actually get the actual sum. And this is the time for you to write in your notes that only geometric and telescoping series are the ones where we know the sum. Okay? For geometric series, you have that formula S equals A over 1 minus R. And for telescoping series, the number that you get at the end is the sum. Because then you just add. So those two are the only two that we are learning today, and those are the only ones that you know the sum for. Everything else that we learn, 8 tests coming up, you will not know what they converge to. You will know they converge, but you have no clue where. Yes?
1 plus 2 and then there's characteristics infinity. That's the equation, right? That is telescoping series.
No, the telescoping series is a procedure. Everything that you see written out is the telescoping series procedure. This is the procedure to see if telescoping. Well, telescoping series is the 1 over n minus 1 over, right? So what changes here? What changes is what's in the parenthesis here, which changes how each one of these looks like. But they will still be canceling, all right? And you might not be able to cancel all of them, right? Depends on what remains. It can converge or diverge depending on the limit at the end, which means I'll have to pick something from the book. So your telescoping series problems are problems 55 to 68 in a textbook. So you have a lot to practice there. And they give you some interesting problems. So how about problem 62, which says summation starts at 1 to infinity of square root of k plus 1 minus square root of k. So you see two of these subtracted. So try this one on your own, using the same method of writing out maybe first 5, writing out the last 4 or 5, cancel a whole bunch of stuff, take the limit, see what happens. Telescoping series can start anywhere, 0, 1, 5, because you are writing out terms. It doesn't matter where it starts.
Well, there's my car. I was wondering where it comes from. For 30 minutes, they were just about reality, and then was talking about getting down. He said, okay, the guys were rolling around, one guy and then, so you have the band, they have that guitar, the bass player, and then, so they almost agree with it.
Are you getting 7?
No.
Good, because that will be wrong. 7 is a wrong answer. So we are going to do the same thing as before. We are going to start with whatever the counter tells us to start. In this case is 1, and keep plugging in. 1 plus 1 is 2, so root 2 minus root 1. The next term is this changes into a 2, so 2 plus 1 is 3, and then a 2. The next changes into a 3, 3 plus 1 is 4, and then 3, 5, and 4, and so on. When you start writing it backwards, okay, we used up k for the problem, so now we switch to n's. It doesn't really matter. So it's going to be square root of n plus 1 minus square root of n. And now, going back, start taking away these values. So root n minus 1. So take away 1 again. So root n minus 1 minus root n. Take 1 away. No, minus 2 over here. Square root of n minus 2. There we go. So now take 1 again. So square root of n minus 2 minus square root of n minus 3, and so on. So now when you start canceling, you have positive root 2, negative root 2. You have positive root 3, negative root 3. You have positive root 4, negative root 4. Going from the back, you have positive root n, negative root n. You have n minus 1, n minus 1. You have n minus 2, n minus 2. And then you know that these guys will also cancel because the pattern shows. So what's left? The summation, the entire thing, is equal to negative square root of 1 plus the limit n going to infinity of a square root of n plus 1, which is 1 plus infinity diverges. Right? That's what I said. Please pay attention. It's clearly look. It's clearly negative. You see right there, negative.
Is this streaming?
It should be. Yep.
Okay.
We have one person watching. Hello, person. That's you? I know. So that's telescoping series. As long as you're able to plug in numbers 1, 2, 3, 4 and compute and then cancel things, right? Now, what happened on my exam that I didn't know and you don't know yet? So this was presented to me in class. I went home, I did 2 or 3 problems of homework. I said this stuff easy, right? Because this was the one I understood. And exam showed up. And this stuff didn't really look like this. So exam was like a summation of 1 over n plus 1 from, let's say, 2 to infinity. All right. Does this converge or diverge? Now you can do this in many different ways when you know all the tests.
Can you scroll just a bit? Yeah.
And
okay. Fine. Yeah. Awesome. Oh, that's very mistake. Okay.
all good?
Wait.
Now the problem says use telescoping series to show whether this one converges or diverges. And you go, where the hell is my subtraction?
You have to get the column, column, whatever it's called, in terms of 1 instead of 2.
No.
You just put a negative near minus.
Nope.
No.
Yeah, that happened. So to add, right, since the procedure is so easy and so memorable, right, there's no issue there. There has to be, there's never free lunch, right? So certain problems will be, you will be able to transform certain problems using partial fraction decomposition. And we already did this problem, guys. It's the first example, right? This is just what could lead into that. So you do the partial fraction decomposition, and you will end up with technically our first example, and then you go on from there. So the problems could be given to you, right? The homework when you take a look at the textbook and the online stuff. They could be given straight up with two sequences subtracted within a series, right? And then you just unleash the procedure, or they could be hidden within this where you have to crank the partial fraction decomposition and then. So that's part one of the evil things that could happen. Part two is the number of terms that you have to write out before you start canceling. Because if you look at this, you're going to say, well, the first parenthesis had the number that I keep. The second parenthesis has the number that I keep, and everything else cancels. Yeah, that happened in the first two examples. The number of terms that you have to keep, which will actually have the numbers that play the role in your answer, depends on a difference between these two. So, if this one is n, and this is n plus 1, the numbers that stay in cancellations will show up in the first two. So if these are 7 apart, you will have to keep 7 terms, and the 8th one is the first that will have a double cancellation. As soon as you get the double cancellation, you can stop writing terms. But if they keep surviving, you have to go to the next one and the next one and the next one. So technically, if I'm to redo this problem, I write the first one. Obviously, I have to keep it because nothing get cancels. Then I write the second one, and then a half cancels. Well, then I have to write this one as well because this 1/3 is still alive, and then that 1/3 dies. I get the first parenthesis with both of these crossed off. Then it's done. At that point, I don't have to write any more terms. 1, 2, 3 from the front means 3 from the back, and that's how you can minimize your work. So you see that when they are 1 apart, you must do 3 from the front, 3 from the back, so that's 6. If they are 2 apart, then you will have to keep 4 and then 4 from the back, because the 4th parenthesis is the first time when they will both cancel. Now, the only way to know this and be comfortable with this is if you do a lot of problems, obviously, to catch that pattern. So, when I took this, unfortunately, I wasn't aware of that. So, I did 3 terms on the front, 3 terms on the back. These damn things were 3 units apart. So my answer was off, because I did not include the parenthesis. Right? All I did is I kept the first number and I canceled everything, but I had to keep this one and that one in my, on the exam. So when the difference between this is 1, those are the fastest, easiest problems because you get 3 terms and then the double cancellation happens. Well, 2 terms and then the third one, double cancellation happens, so you're done. Try to see more. Now, the book has variations. They have 4x plus 1, 4x plus 3. Right? So you gotta think about that and so on. So, all I can say is just, do as many problems as you can, and eventually it will become, I don't want to say easy, but it will become easier for you to know how many terms you have to write out and then go from there. Bueno? Yes?
If the example was 1 over n plus 1 minus 1 over n plus 2, it's still just be a 1 difference.
It is 1 difference, yes, because n plus 1, n plus 2, it's 1 difference between them, yes. I was talking n plus 1, n plus 6, 5 difference, which means 7 terms. It's technically plus 2. The difference plus 2. That's how it goes. Yes?
Would you go brutally on the exam? Or would you
That's
make it
how I roll.
like 12 difference apart?
12 difference apart, which means 14 terms lead in, 14 terms lead out, 28 terms. What's that for you? It's nothing. You just, you put that on. I'll leave 4 pages of test blank for that problem. You have no problem. Oh, the dimension is going to be special test just for you? Yeah. Yeah, don't worry about this. This test is not gonna be here till like a month. So why you worry about this? All right. So I hope, this stuff will not be lost on you. That's it for this lecture. I'm going to shut off the stream and say bye to all the friends there. which is still u.